right, hello everyone. Welcome to our STEM speaker event on living in a materials world, adventures in material science and engineering by Dr. Veronica Augustin, an assistant professor from North Carolina State University. Dr. Augustin received her PhD from UCLA in material science and engineering and is also part of the material science and engineering at North Carolina State University. Her group studies materials at the electrochemical interfaces to aid in the development of clean energy technologies. Before we begin, I would like to take a moment and thank our corporate sponsor, LHC Structural Engineers. LHC is a local engineering firm in Raleigh with more than 40 years of experience designing a diverse number of building structures to include hospitals, churches, corporate buildings, and college and university projects. A few of their notable projects include the Medical School for East Carolina, the North Carolina Museum of Art, the North Carolina Museum of History, and the North Carolina Aquariums at Roanoke Island, Fort Fisher, and Pine Knoll Shores. We are grateful for their funding and support, which makes this speaker series possible here at Wake Tech. Please join me in giving LHC a big round of applause. And I'd like to say that we welcome questions at the end of the talk, and we're very excited to have Dr. Augustin talk about all things material science today, so please join me in welcoming Dr. Augustin.
Thank you so much, Christina, for the invitation, and thank you all for joining me in the classroom today, as well as at the other campuses at Wake Tech. So this is the first time that I'm visiting the campus, and I'm really excited to be here to meet some of the students. I know many of you are thinking about transferring to NC State in the future, and I hope I get to see you there on campus. So what I envision this talk today to be about is kind of a mixture of my personal journey in STEM, how I went through and decided to follow an academic career, as well as my research, or what I actually do at NC State on the Centennial campus where my laboratory is located. So I call this talk Living in a Materials World. If you remember that old Madonna song, Material Girl, it always kind of resonated with me for a different reason, because I became a material scientist and engineer. And I hope through this talk, you not only see kind of how at least one path in STEM was developed, but also what material science and engineering is, which is one of, I think, one of the most critically important engineering fields around today, particularly as we get to the age where we are able to manipulate matter at the atomic level. That impacts all engineering fields, and maybe will inspire you to perhaps check it out when you move on to an engineering school like NC State. So right now I'm an assistant professor of material science and engineering. That means that I just recently started what's called the tenure track at North Carolina State University. It's kind of a grueling process where I basically have 5 years to prove whether I can stay and maintain a externally funded research program that's well recognized in the US and around the world. So really my path, what I'm showing you today, is not the end of any sort of journey by any means of what I'm doing today. So a little bit about me. This is kind of hard to see on here, but this is the globe. I was born over here. This is Poland. I was born here in southwestern Poland. And when I was about 8 years old, my parents basically won a green card lottery to come to the US. This was in 1993. This was the time where the Soviet Union was breaking up, so a lot of uncertainty in that part of the world. And my family made the decision to move from Poland to the US. And we moved to Chicago. And if you've ever been to Chicago, you know that there's a lot of Polish people that live there, and we were one of the families that moved there. But we didn't move into a Polish neighborhood, actually. We moved to a Hispanic neighborhood. And for many years, when I first came to the US, I really didn't know anybody who was actually born in the US. All my friends were from Mexico or India or Pakistan. I thought that's just how, I thought it was wonderful. I had never met people from different countries when I lived in Poland. I grew up in the Chicago area and then made the trek to Arizona, and I'll tell you about that when I get to the part about college. I went to the University of Arizona to study material science and engineering. After that, I moved to graduate school at UCLA over in California, University of California, Los Angeles. And then after you finish your PhD, if you want to become a university professor, there's still a little bit more training you need to prove yourself as a researcher. And I did that at the University of Texas at Austin before I embarked on faculty interviews and decided to make North Carolina my home for the foreseeable future. And I really enjoy living here. I never visited North Carolina before coming here, and I was really amazed at both the natural beauty of this state as well as this wonderful Research Triangle area, which has a lot of opportunities for people in my career field. So the first part of my talk will really be just about my journey to an academic faculty position, and then I'll share with you more technical stuff with my research. So this is a picture of where I was born. It's a town that's very hard to pronounce if you're not from this part of the world. It's called Zgorzelec, Poland. And Zgorzelec has a very interesting history because up until World War II, it was actually a part of Germany. So what you don't see in this picture is there's a river that runs through the town, and the river was used as the border between Germany and Poland after World War II. And the town on the German side is now called Görlitz, and the Polish side is called Zgorzelec. So this is where I grew up. It's a town of about 50,000 people, I think, or so when I was born living there. And it's a very small town, very different from anything in the US. And one thing that I remember very well when I was a kid is that I really loved rocks and minerals. So my parents would always buy us books if we did well on our grades, if we had good report cards. They would always buy us books, and one of the books they bought me was this book, and I actually found a picture of it online. It's in Polish, obviously, but it's called Skały Minerały, which is it was rocks and minerals. And what was exciting to me was to seeing all these beautiful colors, gemstones, things that I couldn't, imagine how it was made or what it could be used for, all these wonderful things. And I would just spend hours looking through this book. And this was one of the things that I remember very distinctly as a kid, thinking that I would love to make this a career in the future, to do something like this, where I was able to work with materials that were beautiful like this. So in 1993, my family moved to the US. We moved to Chicago. This is the beautiful lakeshore of Chicago on Lake Michigan. We moved in the early 90s, so I remember very well when I was a kid watching a lot of Chicago Bulls games, a lot of championship games. It was the era of Michael Jordan and Scottie Pippen and Dennis Rodman. I didn't even really follow sports too much, but if you were in Chicago in the 90s, you were a Bulls fan. When we moved to the US, the reason I wanted to kind of highlight this is that my family, we came without a lot of money. We didn't live, in this part of Chicago. We lived in some outlying suburbs and more difficult situation. And I think the key thing from that is that my siblings and I were the first to go to college in the US. And going to college in the US is very different than going to college in other countries, where in other countries, maybe the college is already paid for by the government. So we were going through this process of selecting colleges and learning about what opportunities are available, kind of charting our pathway through the system. And looking back on this process now, having been in the education system in the US for a very long time, I can see that there's a lot of things we could have done better, come out with a lot less student loans, for example, if we had done different things. And one of those, I think, is really to utilize places like Wake Tech, community college, to help get general education credits and other classes out of the way, because the cost of college these days is very, very expensive. So I definitely applaud those of you that are choosing this route. One of my early heroes when I was growing up was, of course, Marie Curie. From a personal standpoint, it's because she was also born in Poland before moving to France to continue her scientific studies. And one of the things that really impressed me about her was that she had an incredible work ethic. So if you've read about the discovery of radium, which is what she's famous for, it took an incredible amount of work to isolate radium, which is a very small component of uranium containing ores. So basically, she had to take tons of rocks and process them to extract a little bit of radium that came out. And so what this taught me was that, yes, you had to be smart. I mean, she was very, very smart. But there was also a significant work ethic involved in becoming a scientist. And this was important to me because I feel like having a genius may be rare, but working hard is something that all of us are able to do. And that really resonated with me. So this was a very early hero for me when I was starting out in science. Okay, so then going to college, when it was time for me to apply to universities in Chicago, like I was telling you, my family, we were the first ones, my siblings and I, to go to the university process in the US. And we didn't really know a lot about all the opportunities that are available to students, scholarships, need-based scholarships, internships, you know, all the things that you kind of do to get into a university, or even have experiences that universities find important on applications. And when it came time to go to college, I found myself applying to schools that were extremely selective, and nobody was telling me, oh, you know, you should make sure you have some other schools as well and things like that. And so at the end, I was kind of left deciding between going to University of Illinois, which was in-state, in the state that I was living in, or going externally to University of Arizona. And Illinois is a really great engineering school, but at the time, paying pretty much the full cost of a one-year tuition, which is what I was facing, was about the same as going out of state to Arizona. And I decided, you know what, I'm gonna go somewhere really far away and go somewhere very different and learn something about the US and kind of make it on my own, where nobody from my high school would go, and go to Arizona. So that's where I went for my degree. One of the first things I remember when I started undergraduate is that at the time they used to do this thing where during the first few days of being in the College of Engineering, they would tell you, you know, look to your left, look to your right. These people will not be with you at graduation. I think that's a kind of a scary way to start the first week of classes, but that's what people did. I don't know if that's what they still do. I don't think we do that at NC State, but it basically sets this expectation that this is going to be hard and not all of you are worthy enough to get an engineering degree or something like that. I don't want to tell you that, because I think my personal opinion is that as long as you are interested in something, as long as you really want to learn it, you can learn it. There's no doubt about it. So those scare tactics are really, I think, I'm not sure what the intention is, but perhaps they're just thinking about people who maybe never wanted to do a particular field to begin with or something like that. Anyway, what I started off studying at University of Arizona was chemical engineering. And the reason I picked chemical engineering is because I loved chemistry. And chemistry was what I knew from high school. And engineering, I heard, is something that you do when you want to use science and technology to help people. So I thought, well, I like chemistry, I want to do engineering. Chemical engineering sounds like the field for me. Within the first semester at undergraduate, I heard about this field of material science and engineering, and I realized that this is actually what I really wanted to do. Material science and engineering is concerned with the science and engineering, so it's understanding an application field of all the solid state matter around us. And that involves traditionally fields such as metallurgy, so for example, the processing of steel and aluminum, but increasingly it has to do with the science and engineering of what we call advanced materials, and probably the best example we have of that is the processing of silicon. So silicon element, we know a lot more about than we do most other elements on the periodic table. And the reason we know so much about silicon is because it is the critical component that makes our computers work today. And so what is shown in this picture is what's called a single crystal of silicon. So you've probably seen single crystals of diamond, like diamond engagement rings or the Hope diamond at the Smithsonian. That's what we call a single crystal. This is a single crystal of silicon. Imagine a single crystal of diamond that big. This is a single crystal of silicon that is grown in a lab and processed by companies such as Intel. They can cut these silicon crystals, they're cylindrical shaped for a reason, into slices onto which they build the computer chips that are used in all of your everyday devices. So material science and engineering, I view as kind of the foundational engineering field that enables high-tech applications in all other areas of engineering. So this is, for example, how material science can impact the electrical engineering profession. In the case of mechanical engineering, we use single crystal alloys as turbine blades in jet engines. And the reason you want materials that are able to function and are processed at such a high level is that they can lead to better performance. So in material science and engineering, we have this kind of relationship between the chemistry, the structure, processing, and then application of materials in simple applications to very complex applications. So this was kind of when I started to see that material science and engineering, you can actually start to work with materials. A lot of what you do is very tangible. It seemed like the right field for me, and I really fell in love with the topic. However, I would say the first 2 years for me of being an engineer were hard. It was a lot of kind of basic classes, very abstract in some ways. It was hard to necessarily relate what I was learning to this stuff that I heard about I could do down the road in the future. I'd say that a turning point for me in my academic career really came when I got to do research and apply or think about the things that I had learned in the classroom in the lab setting. And my first research opportunity was actually really unique because I was able to do it at Pacific Northwest National Laboratory. So the United States has a wonderful system of federally funded laboratories. Many of them are managed by the Department of Energy, and one of them is Pacific Northwest National Labs, and these national labs often host summer interns. Now, at the time when it came to apply for this opportunity, I actually didn't have any confidence that I would ever get into anything like this. I thought, you know, I'm just a regular engineering student. Why should I work at a DOE lab like this? What do I have that's so special that they needed? And it turned out that I had a professor at University of Arizona, B.G. Potter, and he said, you know, I'm going to Pacific Northwest National Lab this summer. I need a team of students to come with me. Why don't you come with me as one of the students? And I was really shocked at first and really excited that he thought I could do it, because at the time I thought, why me? Of everybody in the classroom, why should I go? And when I was there, what I was working on was something I had never thought about or heard about before, which is the use of arsenic trisulfide, which is a pretty nasty compound. It's arsenic based. That's used for optic applications, specifically for infrared optics. And I was studying the environmental degradation of this material. So I had this little thin films of this material. This is its crystal structure. And I would put them under different color LED lights into an environmental chamber at a particular temperature and humidity to see how this material would degrade over time. And I really loved the lab work. I realized that's what I wanted to do. I wanted to do research. I loved the lab work. Everything after this point, it's like before internship, after an internship. After the internship, everything made a lot more sense for me. I felt like I had a clear pathway and a clear direction, and I really credit my professor at University of Arizona for giving me the confidence to go after something like this, because up until that point, my goal was just to, get through the 4 years and then hopefully get a good paying job to help my family out. And then, so like I was saying, after this experience, I started to think, well, I want to do research, and maybe I could even become a professor in the future. And so this is me on graduation day with my parents. So see, it's in Arizona, so we have the saguaro cacti. There was very hot. It's May in Tucson. But I remember a critical semester where I told one of my favorite professors at Arizona, somebody else, not the person who took me to the DOE lab, that I wanted to become a professor. And he said, why would you ever want to become a professor? when being a mother, a stay-at-home mother, is really the best job that a woman could have. And you can't have it both. And I was really crushed because I had seen faculty being able to do it, and I thought maybe I could be one of them. But I was really, really crushed when he said that to me, and I still remember that comment. And I couldn't believe he would say that, and he meant it, I think, to be helpful. And what it did is, first it made me really upset, then it made me question whether I was really able to do it, and then it made me think, well, you know what, I'm just gonna be, I'm gonna use that as a fuel to do what I want rather than as a reason to stop doing what I wanted to do. So things like this can happen, on your path. People can sometimes give you well-meaning advice that you want to do ultimately, and you can either use it as a reason to stop what you're doing or channel it into a reason to continue on your path. And I'm really glad I did, because I went up going to graduate school at UCLA. It was one of my favorite experiences thus far. I was in LA for about 6 years, so a PhD can take a long time. Mine took a little bit longer, but it was all good because I wanted it to take a little bit longer. And this is my research group at UCLA. This is my PhD advisor, Professor Bruce Dunn. And what I really loved about my PhD advisor is that the way that I connected with him, the way that I found a spot in his group is because I went to a research seminar that he gave at the University of Arizona. And undergraduate students at the time didn't go to many research seminars. And I was one of the few students that actually went, and then I really liked the topic, and I stayed after to talk with the professor, and he said, hey, come show you the lab, we can show you the group. And when it came time for me to apply to grad school in a couple of years, I was able to join this laboratory. So it really came from a meeting, from attending the seminar, that I was given the opportunity to make the connection. And I really credit Professor Bruce Dunn with my development as a scientist. And kind of a different story of what happens when people give you advice is that about 4 or 5 years into my PhD, Professor Dunn called me into his office and said, okay, Veronica, it's time for you to start thinking about what you're going to do when you graduate. What do you want to do? And by that point, I had had some industry research experience. I did an internship at a research lab in Malibu, California, and I thought, hey, that would be pretty sweet to be a research scientist in Malibu, make pretty good money, live in California. I think that's kind of where I will set my sights. And he said to me, before you even say anything, I think you should become a university professor. And I was, again, taken aback because I thought, really, why me? Why should I do this? All this stuff, all the confidence issues came up again. But this is just the reason I wanted to tell you this is that you will get different advice as you go through the STEM career, and you kind of have to figure out which one do you take to heart. And I took the advice from my PhD advisor to heart for sure. But what's shown here on the bottom right is a picture of one of the materials. This is, again, a crystal structure of one of the materials that I worked with. And this at UCLA is when I started working in the area of electrochemistry, which was what became my area of research that I'm doing at NC State today. One other thing I wanted to share with you is that during this time that I was going through my graduate training, I became aware that science is not just about being in the lab and doing the work that we're doing in the lab. It's really about going outside and also mentoring other students, traveling to other countries, meeting with their scientists, making sure that our work, whatever we're doing in the lab, is translatable to a broader audience. Not necessarily in terms of products, which is really challenging when you're working in a university, but in terms of understanding, in terms of showing what it is that we're doing in the universities. So this is a picture of an opportunity I had to travel to Ethiopia when I was a graduate school. When I was a graduate student. This was funded through the National Science Foundation, and this is me with students from Rutgers University, as well as from Makerere University in Uganda and the universities in Ethiopia, working on looking at solar cell experimental results. So this is us during this workshop. And on the bottom right is I'm working on an outreach project with some students at the University of Texas, where we're making some low-cost experiments to demonstrate science topics to students in African universities. So like I was telling you, after I did my PhD, I had to 4 years doing additional training to prove myself as a researcher. And this part is kind of unique to academia. I could have gone into an industry job right away, but I took this additional training so that I could become competitive for faculty positions. And the reason that this is unique and important for a faculty career is that what usually happens is that you will move to another institution and to another advisor to work with them. And you have to basically start an entirely new project and show that you can do that, because that's kind of what you do when you become a professor. You have to start from scratch all over again. So I went to the University of Texas at Austin, which has one of the premier programs in electrochemistry in the US. And this is with my group. So now this is a much larger group. My advisor, Professor Rumugam Mantharam, is not in this picture, but it was a much larger group, a different university, and a different project where now I was working on electrocatalysis, and this is just showing what happens on the surface of a material when it's undergoing what's called the oxygen evolution reaction. So I learned a new topic and worked with new materials. Okay, so then after that experience, which was about a 2-year experience at University of Texas, I started applying to university positions around the US. And right now, university hiring is extremely competitive. For each position, it's easily going to be over 100 applicants that will apply. And I was very lucky to land a position at NC State and be very well supported at NC State to start my research program. So now I'm in the position of being the PI, and these are some of my students, both graduate students and undergraduate students. So at NC State, because I'm running a research lab, undergraduate students in the department are able to work with me as undergraduate research assistants. And the students that are in this picture have all, the undergraduate students have actually graduated since then. They've gone on to grad school at Clemson, Caltech, and University of Virginia. And I'm really excited for them and looking forward to what they're gonna do as they kind of move in their careers. So just a few things that I would like to share with you, what I've learned as I've kind of navigated this process from being in a situation where I had to basically pay for college myself, or find ways of paying for college myself that involved student loans for the most part, to where I am now as a faculty at NC State, is that first of all, you can learn anything you want to learn. I think particularly at the level that we're at now, graduate students to join my lab, I make sure they have some minimum requirements of GPA or GRE, but I do not view those scores as really an indication of success in research. And I think that's actually been shown now that something like the GRE test that's taken for graduate education is not necessarily, how well you do on that is not necessarily an indicator of how well you will do in the lab. And I think part of it is that if you are very successful in the classroom, the environment of a lab may prove to be a little bit confusing or difficult, particularly the part where you're dealing with failure a lot. You will have research projects that will go nowhere, and you will have research projects that will take to work. And how to deal with that can be challenging. So really, I think hard work and perseverance, resilience are more important than any kind of raw talent that you may have to start with. And that's something that we can all work with, and you can really learn anything you want to learn, whether it's engineering or any other field. The best way to obtain opportunities in today's world is really through networking. So I really encourage you to go to as many events, opportunities to meet prospective employers as possible, because you never know where the next opportunity could come from. I would not have known that when I went to the seminar by Bruce Dunn at UCLA that he would become my graduate advisor down the road. And so you just never know what happens. is key. These days, that also means having some kind of social online presence through LinkedIn and things like that. You want to be searchable. People need to be able to find who you are online. Take advantage of as many opportunities to learn as possible. So if there are opportunities to apply for internship or to take research positions, take them. I didn't mention this here, but my first job in the lab at Arizona wasn't really the internship opportunity I had at the DOE. That was my first research position. But my first job in the lab was really the old, washing glassware, nitrogen for an electron microscope, and washing the tools every day. That's what I was doing. I was happy to get paid a little bit for doing it because I had to, pretty much pay for college myself. So take advantage of as many opportunities to learn. If you hear about something cool, jump on it. That's how I got to go to Ethiopia. I heard, we're taking applications to go to take students funded by the NSF to Ethiopia. I knew my application was going to be one of the first ones in because that's just something that I really wanted to take advantage. Look up to the right role models, whoever these people are for you. I think, set the bar for what they've achieved and try to meet them. Of course, some people might view it as like, okay, I'm going to pick the Nobel Prize winner Marie Curie as my role model. But it could also be someone like a professor, in my case, more senior faculty than me at NC State or other universities who are doing the kind of research or having the kind of career or the work-life balance that I would like to have. Because when you see what's possible through people like that, I think it really makes it seem more feasible for me to do it. And I think it's important to listen to all advice, including criticisms, but you have to know what to take to heart. So I told you a couple stories, times where I've been told not to do something, that it won't be as rewarding as I think it will be, to times where I was encouraged to do something. And you have to kind of discern what to take to heart. That's a difficult part of this process, having confidence in yourself. But I think as you go through this, as you go through your own career, particularly in the sciences, through these research opportunities, each experience kind of builds upon itself so that you get a little more confident each time. So now I'm going to switch gears and talk about what I actually do at NC State, my day-to-day life in the lab, and what motivates my work, because this is what I think about most of the time. I teach class as well, but most of my time is spent on research and mentoring my graduate students. So what motivates me as an engineer is the need for sustainable energy. This is a graphic from NASA from last year showing the amount of carbon dioxide parts per million in the atmosphere as a function of thousands of years before today, where zero is given 1950. And you can see where we are today. We've actually passed this 400 ppm of carbon dioxide in the atmosphere since then. And what this means from this chart, so again, this is in terms of 1,000 years before today, is that we're living in an unprecedented time of the amount of carbon dioxide that is in the Earth's atmosphere. So those of you that have friends and family in Houston, my brother lives in Houston right now, the devastation that's experienced through storms that people have never seen before, like Harvey, we can attribute to the strengthening of hurricanes, as scientists have predicted will happen when global temperatures start to increase, particularly when bodies of water become warmer. So, all my prayers, my thoughts go out to people in Houston right now, because I really don't know what the solution is for cities like that, Houston, Miami, that are in low-lying areas that are just very prone to these flooding events that were predicted to get worse. This need for sustainable energy, that's from the what's happening now with existing fossil fuel emissions into the atmosphere, and then what's coming in decades. So when it comes to countries like the US, we're the major users of energy in the world today, China, countries like the US and Europe, our energy use is predicted to stay more or less flat for the coming decades. That's because population growth in these areas is not going to be increasing, and because electricity is already abundant in this part of the world. However, this red bars projected increase in energy use coming from developing countries around the world. So that's India, China, Sub-Saharan Africa, South America. This is data coming from the US Energy Information Administration. So this picture here, it's hard to see, it's also from NASA. It's the world at night, and what it shows you is that there's areas of the world that are well lit up, such as the US, Western Europe here, North Korea, Japan, etc. But there's also large areas of the world that are dark, and we know that people living in those parts of the world, they need electricity. It's a fundamental component of human development. And so we shouldn't stop them from accessing that electricity. The question is, can we do so sustainably? So we have this kind of perfect storm of factors coming together: increased environmental effects of fossil fuel emission, along with increased energy generation, energy use rather, around the world. So how do we solve that problem? That's a really big engineering problem. It's a grand challenge according to the National Academy of Engineers. One thing I do before I launch into the research that I do in my lab is that I told you I had a chance to go to Africa when I was a graduate student. That was in 2012. And when I was there, I got to connect with scientists from Sub-Saharan Africa. And what I learned there is that people that live in Uganda, for example, most of them live very agrarian lifestyles still, so many farmers, and they're very aware that their climate is changing. Is changing, and that they need to think about how to develop their country in a sustainable manner. Now, their challenge is how to do so, or what's the best way of doing that in a resource-poor environment. And so what I do is I work with students at North Carolina State University. Actually, the students there are the leads on this project, to develop experiment kits to demonstrate how to what sustainable energy devices are out there and how they could be used in the future. So this is an example of an aluminum air battery, which is a type of a battery that uses air, ambient air, to chemical energy into electricity. So this very simple battery is powering a blue LED here. We send experiments like this, which are very hands-on ways to demonstrate fundamental concepts that are related to sustainable energy technologies, to universities in East Africa. So these are students that we work with in Uganda, and this is my collaborator, John Paul Oneku, who I met when I was a graduate student. And then what's really cool is that the students here, they did this experiment in their classroom, and they were really excited about it because they got to see what ITO glass is, which is a transparent electronic conductor. They were excited just by being able to see something like that. They went from doing this experiment in their classroom to a couple of weeks later demonstrating this concept of a solar cell to their local community at a World Science Day at their university. So this is kind of a way of paying things forward, and this is something that isn't just restricted to NC State. And if you're interested, you can check out our website and our Facebook page. We've been collaborating in Raleigh with Shaw University, some of their students there, but it's really open to anybody who wants to kind of join in and join our building sessions, help us write experiment kit procedures, things like that. So my research, as you might have guessed by now, is on electrochemical energy storage and conversion. The way that this field got started is way back in 1800 through the first batteries. Were very, very simple. They were called voltapiles. You take two metals together, separate them by some kind of an ionic conductor. It could be salt water in a piece of cardboard, and you have yourself a battery, which is going to convert chemical to electrical energy. And what was really interesting is that the battery, which was developed in 1800, this voltapile, for the first 100 years or so, what it was used for most often was for scientific experiments. So it was a scientific tool. It wasn't used to actually power, any kind of personal devices, because they didn't exist. So first, it was to demonstrate the electrolysis of water. the existence of a series of elements by Sir Humphrey Davy. In just a span of a year, he invented 1, 2, 3, 4, 5, 6, 7. He discovered 7 elements. You know, that's kind of hard to do that these days. By Michael Faraday, who discovered the first and second laws of electrolysis, demonstrate the first fuel cells. And then it wasn't really until the 20th century when they start powering electronic devices that we start to see batteries doing the kind of function that we think of as today. This is just to show you the timeline of scientific discovery. What we call kind of basic research sometimes has no apparent application in mind. It may take decades or 50 or 100 years to see something actually come to fruition. So electrochemical energy storage is a particular type of a device where we have reversible electrical to chemical energy conversion. An example of that is a lithium-ion battery, which probably all of you in this classroom have. The one statistic I saw recently said that there's at least one cell phone for every person on the planet, and all of those cell phones are powered by lithium-ion batteries. It's a huge technological success story. And the way that these batteries work is really very simple. They're also called rocking chair batteries. They take lithium ions from the anode to the cathode, or vice versa, depending on whether you're charging or discharging the battery. And the anode and the cathode are what we call layered materials. So they literally have layers of atoms. And the lithium ions can nestle in between the layers. And the key to being reversible is that we can change where the direction of where the lithium ions want to go by just changing the applied potential on these electrodes. And so the reversibility to electrochemical energy storage is key. And the example of the anode and cathode materials is that we use graphite for the anode side. So this is this kind of graphene-like layers nestled here. We use graphite for the anode material and a lithium metal oxide for the cathode material. But the basic thing is that both of these are what we call layered materials, and the lithium ions just kind of shuttle back and forth depending on whether you're charging or discharging the battery. One thing to keep in mind with these lithium-ion batteries is that these are lithium-ion. At no point do you ever form a lithium metal unless something goes wrong. So this was a big change from the very first lithium batteries that were developed in the 1970s, which did use lithium metal and had a lot of safety issues. We don't use lithium metal in the commercial batteries that you have in your cell phones today. The lithium is always in the Li+ state, just how it is when you take sodium chloride table salt, you dissolve it in water, you have Na+ in its ionized state, which is very different from sodium metal, which is a very air-sensitive metal, just like lithium is. So electrochemistry, kind of one of the things that I like about it, it's an interfacial science. So that means that a lot of the action takes place. If you think about a stage in a theater, a lot of the action takes place, on the electrode surface. That's the stage, and storage, electrochemical energy storage, like batteries, where we can look at very complex ways of tuning our electrode materials, maybe to have particular shapes of materials, is shown here. There's also energy conversion, which I won't get into the details of, but electrochemical energy conversion is how we can use electricity to drive a chemical reaction. One of those reactions that we're interested in is how do we split water into hydrogen gas and oxygen gas, hydrogen gas being a very, very energy-dense fuel that we can then use to power a fuel cell, for example. So electrochemistry is an interfacial science, meaning that a lot of the action happens on the surface of the electrode. We study the surfaces of these materials on the electrodes, but it's also an interdisciplinary science. So that means that as you study this area, you will become very familiar with chemistry, material science, surface science, engineering, like electrical engineering, physics, mechanical engineering and mechanics, even biology, because there are things like biofuel cells, which is basically trying to engineer a biological system to convert energy. So for example, using some kind of enzymes or bacteria to do the work of converting chemical energy to electricity. or vice versa. Electrochemical energy technologies, today's world, portable electronics, your cell phones, your laptops have been a huge success story. They're also used in some other devices. For example, if you drive a car, virtually all cars have these lead acid batteries, which are also rechargeable batteries, but they're based on lead, so they're much, much heavier than the lithium-ion batteries that we put into our cell phones and laptops. In the present today, I think we can also say that we have vehicles. It's really not a question. Electric vehicles will become a part of our transportation grid, but just how quickly are they going to grow? So companies like Tesla have really done a tremendous job of pushing that market forward. There's also talk of doing electrification of commercial vehicles, where it could make a lot of sense for, especially since these types of vehicles can be recharged during what's called regenerative braking. In the future, so where does the sustainable energy come into play with electrochemical energy technologies? It comes into play when we think about sustainable energy from the form of photovoltaics or wind turbines, which are both intermittent ways of capturing energy from sunlight or wind. What do you do at night? What do you do when the wind doesn't blow? You need to have some way of storing that energy until you need to use it. So one way you can do that is through a battery bank. So Tesla is also selling this type of a product called a Powerwall, I believe, which is just a lithium-ion battery bank that you can have in your house, and you can use it to basically charge it with electricity from a solar cell. Another option is to, instead of just doing energy storage, is to have electrolyzer in your basement. So you have a tank of water in the basement, and this tank of water is you're passing a potential between two electrodes and forming hydrogen and oxygen gas. The hydrogen gas is a very energy dense fuel that you can then use to run through a fuel cell, which takes the gases, recombines them to form water. We get electricity from that. That electricity can be used to power your vehicle or your lights in the house, whatever it is. So electrochemistry, the way that we have of going between chemical and electrical energy and electrochemistry, is a very important component of future sustainable technologies and today's electronic devices. My argument is that all of these applications are currently limited by materials. So for example, having a cheaper battery for the Tesla, or having a battery on your cell phone that will let it last for a week instead of for just a day. All of these things are currently limited by the materials. And so some of the questions that we're dealing with is, how do we get higher energy density? So how much energy is actually stored in the device per unit volume or area or weight. To do that, we can move beyond what are called intercalation reactions. The intercalation reactions is what happens when the lithium ions just kind of nestle into an empty site of the material, like those layered materials, but the structure of those materials doesn't change very much. We can go to higher energy densities if we move beyond those mechanisms. We want higher power densities, so how quickly can we store energy in the material is really dependent upon how quickly we can move lithium ions or other ions between the two electrodes. We want to have better safety. And so when there's a battery fire, that is a high profile event. Increasingly, we find that some of these events are happening on aircraft. So you might remember that the Boeing Dreamliner was grounded because of issues with the lithium-ion batteries. There's also incidences of people on flights, watching a movie or doing something that's taking up a lot of current, leading to battery fires. So how do we make batteries that will not result in a catastrophic failure, that are foolproof, that will shut down if there's a heat excursion? That's an important component of today's research in this field. How do we improve lifetime? So for a cell phone, we may be okay with having the battery last for 2 years, because maybe in 2 years you want to get a new phone. But if you have a car, or if you have a huge bank of batteries in your house, it will be very expensive to have to change those every 2 years. We need batteries that can last for 10 years or 20 years. They're not there yet. And we want to decrease the cost as well by moving away from rare transition metals. So you might remember my early kind of fascination with gemstones and minerals, and it turns out that there's certain types of materials that we use in the battery world that are based on very rare and beautiful transition metals such as cobalt. And how do we move away from that from a cost standpoint and also from an environmental standpoint? So what I'll show you just in the interest of time really quickly is that one of the things that my group works on is how do we get energy storage to be faster? Because in some applications, you might want to charge your device in a minute or have it discharge in a minute. Batteries, for fundamental reasons, are good at storing energy, but are not able to be charged or discharged very quickly. So this is a plot of power versus energy, how much energy can be delivered versus how quickly it can be delivered. And what this chart shows you is that there's batteries down here and there's capacitors up here, and you either can have high energy and low power or low energy and high power. So we have this issue. And whenever you have this kind of separation, if you're a scientist or engineer, you want to know, well, why can't I have something up here? Why can't I have both energy and high power? What are the limitations for that? And so I've been working in this area of electrochemical capacitors, which are devices that people usually aren't as familiar with as batteries. And these devices are really interesting because they really take advantage of the interface of a material at the electrolyte to store charge, more so than just the bulk. And won't have time to get into the details of this, but there's different ways of utilizing these electrochemical capacitors. The basic one are these double layer capacitors, which is really just electrostatic charging at the electrode-electrolyte interface. And then these different types of capacitors called pseudocapacitors, which now actually have redox reactions happening that lead to faster capability. So what my group is doing at NC State right now is we're looking at materials that are layered, just like the ones that are utilized in today's batteries. But what we have in between the layers is some kind of a fluid or solvent molecule. So it could be water, it could be another type of solvent. And the reason we're interested in these is that we think that having this, what we call confined or nano-confined fluid, could lead to some very beneficial properties. And fundamental science questions could be answered about what actually happens when an ion moves into this kind of a layered environment. What I wanted to kind of highlight for you from work that we're doing is that in materials science and engineering, we're really at the level where this is how we think of engineering devices around us. You know, it's not just about kind of the macroscopic object that you have in your cell phone. It's really about thinking of it on this atomic level. So in these pictures, these blue spheres represent oxygen atoms. And inside of this shape here is supposed to be a transition metal cation. So we're really thinking about engineering and doing science with materials at this level. And all of our work is kind of focused on this scale. So just as an example of this process, this is an electron microscopy image of one of the materials that we're studying, where we're able to visualize layers of the material that have a spacing of 6.9 angstroms. So this scale bar here is 10 nanometers. This is the type of stuff that we're interested in. And then looking at this material, not just characterizing its properties, but looking at what happens when we do electrochemistry with it, and then what does that mean for applications. So I didn't really have time to go over all of these details with you of the research. I just wanted to show you this is what we do, this is what we spend a lot of our time on. We make materials, we characterize them using advanced techniques that can tell us something about the atomic scale structure. We do electrochemistry with them, and that process is usually kind of back and forth, back and forth. The work, kind of as indicated on here, is very collaborative, both with universities outside of NC State, as well as faculty and groups at NC State. And then my time really as a professor now, I'd say the most important thing that I'm doing is really working with my students here, making sure that they have everything they need to complete their PhDs and their undergraduate degrees. So really, from my end, that means making sure that they have money to do so. To keep in mind that I told you that I needed to get student loans to finish my undergraduate degree. One reason that I was able to go to grad school is because I had a research assistantship that was paid for through federal research grants. And in science and engineering, when you go to graduate school for a PhD, that PhD will be paid for through some kind of fellowship or external grant. So student loans were not involved in that second part of my training, and just something to keep in mind if you're considering going in that direction in the future. So with this, I'd like to end, and I'm happy to take questions from you guys and folks at the other campuses. Thank you.
If there's a question in the room,
Okay, any questions? Yes, in the back.
What are your thoughts on the electric vehicles as far as, yes, they could be more beneficial in the future, but as far as their productions now with all the fuels that are being used to get those materials to make the vehicles, what are your thoughts on that?
So the question was about electric vehicles and recognizing that it takes energy and perhaps rare metals to make them happen. Is that kind of correct? Yeah, this is a really important point. I think that as we hopefully start to see increased penetration of electric vehicles, the question of battery recycling will come into play. And that is a challenging issue, but one that is being dealt with by the Department of Energy National Lab. So they have scientists actually predicting and figuring out what are the best ways that we can recover transition metals or aluminum, whatever it may be that's worth recovering from batteries, because one thing we're not doing a lot of right now is lithium-ion battery recycling. However, if we take a look at something like lead-acid batteries, which have a very high recycling rate, that is a goal to kind of go towards, and that's one where we get more and more volume of vehicles in the road. I think right now we're still kind of in the early stages, and it's kind of dependent upon how quickly we scale up. But that's a very important point, and a good point to keep in mind is that nothing is free of energy costs, even technologies that can enable sustainable energy. Yeah.
So I know lithium-ion batteries, it's a big thing for you. But what about, is there a difference between lithium polymer batteries? Because I know in robotics and control hobbies, that's a big difference, like battery-wise, if that's what they commonly use. So what's the difference there? Okay, so the question was about the difference between lithium-ion batteries and lithium polymer batteries. They're really the same thing. Lithium-ion batteries, I'm using it as a kind of a broad term. Lithium polymer batteries just refers to the fact that in those batteries, the electrolyte contains a polymer instead of just mostly a liquid electrolyte with what we call a separator, a very thin polymer sheet in between. So I'm really using it as kind of an envelope term to describe that. You mentioned lithium-ion batteries is something that we're focused on. In my group, we're also looking at what are called beyond lithium-ion batteries. So questions about do we have enough lithium in the world for everybody to have a lithium-ion vehicle, or do we have enough lithium in the world to power large-scale power grids that contain solar cells? With questions like that, we naturally start to think, well, why are we limited to lithium? Can we go to sodium? What about magnesium, aluminum? So that's what we call this beyond lithium-ion battery field. My group is working on that, as well as many people around the world. And some of the most interesting ions right now are sodium ions, kind of the next one in the periodic table. Sodium is very abundant. So we could see that coming within the next 10 years. And then maybe another 20, 30 years down the road, perhaps magnesium ions, aluminum ions, and so forth. But it's very interesting chemistry that comes into play when you start to change what the ion is that you're actually trying to store. Yeah, go ahead.
all right, we do have a question from down. How will artificial intelligence impact your field?
How will artificial intelligence impact the field? That's a good question. So I think artificial intelligence has the potential to impact all fields of science and technology. If you're thinking of it in terms of things like machine learning, self-driving cars are actually very well suited for electric vehicles because of the, I think, systems integration between an electric engine and then the computers that has to drive that kind of car. So it could have a lot of applications that way. I think right now what we're seeing is that machine learning is coming into play when it comes to designing new materials and new electrode systems. Hope that kind of answered the question. Anything else? Yes.
Do you have any suggestions on what you could do with the lithium battery in phones, or like, is there any option for recycling today?
So the question was about how do we recycle lithium-ion batteries today? I think you should check in with the manufacturer of the cell phone. There are opportunities. I think there's people that will buy the phones from you, and whether they are disassembled and stripped for parts, which is what I think happens with Apple, might be wrong, or reused and sent to other countries. That's probably the best way to do it. I don't know of any kind of, besides the manufacturers, I don't know of any larger scale kind of businesses that do this. And I'll tell you, one of the reasons this happens is that the chemistry of the lithium-ion battery is quite complex, and that will dictate how you would want to recycle it or what components you would want to recycle. So even though they're all called lithium-ion batteries, some of them might contain more cobalt than others. Some of them might contain more manganese than others. Some of them might even contain some silicon. Some of them might have different kinds of electrolytes in them. So those variabilities from supplier to supplier is what makes it kind of a, where it's best to just send it back kind of down that particular channel, as opposed to the more broad-based recycling we have for lead acid batteries today. Yes?
Can you go back to like one of your previous slides with the developing countries and the energy that will be predicted to be used in the developing countries? So is the goal to that is to integrate more energy saving techniques into those countries before they, start using a whole bunch? Is that the goal?
Right. So the question is, what's the goal of for countries that are going to be coming online with their with increasing their energy consumption in the coming decades? And this is a really interesting question because as far as I know, and I think as far as we all know, each country is a sovereign state, and how they choose to pursue their electrification, how they choose to deliver electricity to their constituents is really a decision that those countries will decide within themselves. I think there's hope that international agreements like the Paris Climate Change Agreement will drive the world to kind of, for each place to consider this issue and try to do so sustainably. But that is the goal, is to have more sustainability in countries that will be increasing their energy consumption. And there is one interesting statistic that I didn't put on here, which is that countries have now surpassed the capacity of renewable energy generation than developed countries like the US, meaning that they are inching ahead of us in terms of how much capacity they're installing that's renewable. Most of that right now is coming from hydroelectric dams, which is considered a renewable energy source. Of course, it's limited by geography, but increasingly that's going to become these solar cells and photovoltaics. So what some people are predicting, what countries like countries in sub-Saharan Africa could do, is they could leapfrog over, for example, coal power plants. Maybe they'll go to solar plants, maybe they'll go to natural gas, but they could leapfrog over older technologies the way that many of people in those countries leapfrogged over landlines, right? So in this part of the world, people have cell phones. In Uganda, in Tanzania, they may never have had a landline. So the goal is that if these technologies become better and better and make more sense for a particular region, that they will be able to leapfrog that. Of course, that I think all depends upon the cost of these technologies, the global cooperation for helping support resource poor nations for making investments in that direction and so forth.
Yeah, because that was my next question. Like, wouldn't that be those energy saving? Aren't they highly, really expensive for developing countries? So.
Right. So the cost of these renewable energies for developing countries can be an issue. There is something that another statistic that I don't have on here, which is the cost of silicon photovoltaics over the past 30 years has seen a very precipitous decrease in the cost per kilowatt hour. I think it's extremely. I don't think people could have predicted how it could fall. So I think it's very promising, I think, if we go in that direction. But I think it really depends upon international cooperation to kind of make that an incentive for people to move in that direction, as opposed to going towards more coal-burning power plants. Because the key thing is this chart right here and all of the effects that we know come from this. So, if we have increasing CO2 in the atmosphere from all of us that are already using a lot of energy, then what's going to happen when we add more people online? And we can't really stop them, and we shouldn't, because electricity, again, is a part of human development. Okay, thank you all for your questions. Very interesting.
I'd also like to say that if you are interested in undergraduate research here at Wake Tech, please contact Dr. Jackie Swanek at jtswanek@waketech.edu with your name and your interests, okay? So if you're interested in undergraduate research. Okay, thank you. Thank you so much.
You're welcome.